Cascade Control. We're going to have a quick recap of feedback control and see why it might not be completely adequate in every situation and how Cascade Control can actually help. Then we'll see some examples of Cascade Control and why they help, and see a particular example that I'm very interested in using servos with triple Cascade Control. Most of the time you don't see triple cascade, you see, just a simple cascade, but you'll see what that means here in a minute. So in classic feedback control, all you really do is measure something you want to control. The controller then decides, based on the error, how big it is, how long it's been around, and its rate of change, PID, how to manipulate the control variable that then affects the process and makes the process react. The problem with this, of course, is some disturbances are very effective on the process. They change the process a lot. And you can't really do much with the process until to correct it, until the disturbance has caused a significant change in the process of some kind. Maybe an error over a long time, or a really quick change in the error, or a large error. So with classic feedback control, the problem is that it doesn't control exactly on set point. It can't. Here's a simple example of feedback control where what we've got is some air that's being blown through some media that's wet. And we're trying to dry this media, and so we put wet feed in and I guess blow air through it, dry air through it, that's been heated up, so that it can sort of dry out and absorb some of the moisture from whatever the feed is, and then the dry product is withdrawn continuously. So the way you make the air warm is with steam. So process steam goes through a heat exchanger. You can see it there. There's a valve for controlling the flow rate of the steam. You can see the air coming in from the left goes through a filter, then through a blower, and it does not, of course, mix with the steam. It just picks up heat from the steam in the heat exchanger, and then goes up into the column there to flow through whatever the medium is that needs to be dried, and presumably picks up a lot of water and comes out, as humid air out the top of the stack. Now the TC1 is temperature controller 1, and what it does is it measures the temperature of the gases coming out of the stack and tries to maintain that temperature at a certain amount by adjusting the steam flow rate. The only problem with that is, let's say that we have some variation in the air coming in. After all, this is, say, just air from outside. Maybe it has a higher water content, it's harder to heat up, or maybe it is at a lower temperature or something, and we need more steam in order to heat up the air so that it comes up to a high enough temperature to actually do its job and pull all the water out of this wet feed. Now, we don't want to overheat the air, because if we overheat the air, as the air leaves, it will just have extra energy in it. It'll pick up all the water, dry out the stuff, the feed we're trying to dry out, but it'll have extra energy, and that's a waste. That's a waste of steam. That costs money. So we want to limit the temperature coming out the top, but that may not be so easy, because if you think about it, you realize it's going to take quite a while for this air to work its way through all this medium and come out. So there's a disturbance variable that we're not dealing with very quickly. The disturbance variable is, say, air temperature. And we're not dealing with it until it's really kind of too late. So how could we affect this? Well, or the steam temperature could vary, right? That's another possibility. Air temperature could vary. Something happens in the heating of the air where the air temperature is not exactly what we think it should be or expect it to be. Now, we always prefer to have cascade control over feed-forward control. It's better if it's possible, but it's not always possible. In fact, there's a distinction between feed-forward and cascade control. The key difference is that in cascade control, we measure something that we can do something about with the control variable we already manipulate. In feed-forward control, we measure a variable that there's not a thing in the world we can do about it. We can just try to pre-compensate for it. That's the key difference between cascade and feed-forward control. So the control variable in a cascade situation can compensate for the disturbance and sort of shield the primary loop from the disturbance. So in cascade control, we really have two controllers. There's the secondary controller, and the primary controller. The primary controller provides the set point for the secondary. So the secondary's job is to make the control variable affect what we're going to measure, which we weren't before, that has all the disturbance in it, and reject that disturbance for the sake of the primary controller, which is measuring the process variable we actually care about. So in our dryer example, you'll notice that now we've got two controllers, TC1A, TC1B. TC1B is the secondary or slave controller. Terminology: primary master outer loop is terminology for TC1A, or secondary slave inner loop is terminology for the cascaded controller, the one in the inner loop. And so TC1B is that secondary controller, and what it does is it measures the temperature of the air before the air goes into the dryer. See, that's where we can reject disturbances like variations in steam temperature or variations in air pressure. If we measure the temperature of the air before it goes into the dryer, we can do something about it, right? That's what our control variable can do. We can crank up the steam flow rate if the air temperature is a little low, or if the steam temperature is a little low, we can give it more steam and thereby increase the temperature before the air actually goes into the dryer. And that shields all those disturbances from the primary controller, so the primary controller just gets to concentrate on controlling the final temperature, the thing we actually care about. Now, one thing really important about this, Cascade Control does not work well unless the inner loop is a lot faster than the outer loop. So the time constant of the inner loop times 10 should be about the time constant of the outer loop, or in other words, the inner loop should be about 10 times faster, or take a tenth of the time that the outer loop takes to respond. So it has to respond quickly, and of course in this case it makes sense that the inner loop would respond very quickly, whereas the outer loop would have a lot of lag in it because of the air moving through the dryer and taking a long time to get to the other side and come out the stack with its temperature. So it's really important that the inner loop be about 10 times faster than the outer loop. In other words, have a time constant about 1/10 of the outer loop's time constant. So basically the inner loop shields the outer loop from disturbances. But one thing you have to do when you're tuning these things, you have to tune the inner loop first. You cannot tune the outer loop until you have good response, good behavior of the inner loop. So the inner loop, in this case TC1B, has to be tuned so that it can control the temperature of the air and do a good job of it before you ever try to tune TC1A. So here's a practical Cascade Control example where we're just making some steam. And so we've got feed water flowing into the mud drum and being heated up, going through the riser tube into the steam drum, where steam is extracted off the top. Now, this is a cascade example where all of the control lines are pneumatic lines. That's why there's two dashes through each line. And it can be a little bit difficult to see which loop is which and what's going on. The flow indicating controller is actually the inner loop, and the level indicating controller is the outer loop. If we add some color to the inner loop, red lines, you can see that the flow indicating controller measures the flow rate from flow transmitter FT and then adjusts the air operated control valve in order to control the flow rate of the feed water coming into this evaporator. Now, where does the flow indicating controller get its set point from? Well, it gets it from the level indicating controller, and the level controller's job is to control the level in the steam drum. So it measures the level in the steam drum from level transmitter LT, sends that information to level indicating controller LIC, which then decides on a set point and sends that on to the flow indicating controller. Obviously, the flow rate into this system will determine the level in the steam drum. But if there's a variation in the pressure of the feed water, it's going to take a while for us to see a difference in the level in the steam drum and know to change the flow coming in. So the flow indicating controller rejects that sort of disturbance for the sake of the level indicating controller and automatically adjusts the flow rate to whatever the level indicating controller requires. Now notice one other thing here. The air operated control valve, these things are notoriously non-linear. So another thing that the flow indicating controller can do is actually shield the level indicating controller from the nonlinearity of the inner loop, which can be a big advantage also and make it easier to control. Another example of cascade control is actually a triple cascade. So what we've got here is a motor where we're trying to control the position of an elevator platform, but controlling position by itself is not enough. Actually, other characteristics of the elevator would be acceleration and velocity. And so the most inner loop here controls the current going to the motor, the current's typically proportional to the torque in the motor, depending on the kind of motor, but essentially you can say that for many kinds. And so if we control the current going into the electric motor, and that's all we do in order to control position, we would actually end up with a runaway system, because at any level of current that generates some torque. Torque then generates angular acceleration, which means that the system would go faster and faster. The position would move away faster and faster. So any level of current would actually make this a runaway system. By turning it into a cascade system, we get rid of that runaway characteristic, because we've got a velocity controller requesting a certain amount of current from the power controller in order to generate a particular velocity as measured by the tachometer. But then the position controller is cascaded into the velocity controller and requests a certain velocity in order to achieve a particular position of the elevator from the position sensor there. So you can see how we're measuring three different variables here: the current, the velocity, and position, and have a cascaded setup in order to control all three. Now this can make the control of the elevator much better. It can do all sorts of things. In fact, you can limit jerk and make smooth motion here, which can it's useful not just for people to feel comfortable, but for many other things as well. So this is an example of a triple cascade setup. So we considered feedback control and then realized how disturbance variables, if they can be affected by the control variable we already have, then a cascade control loop can be superior to a feedback control loop if the inner loop is about 10 times faster than the outer loop. Then we saw some cascade control examples, and in particular a triple cascade control example.